The next reaction intermediate that we're going to be learning about is carbanion. We learned about carbocation in the previous video. So carbanion is also formed by a heterolytic fission. And the only difference between a carbocation and a carbanion is the fact that in case of a carbanion, it has negative charge and it has 8 electrons in its valence shell. So the carbon will have 8 electrons in its valence shell. So here, let's take for example CH3Z, and Z is less electronegative than carbon. So this pair of electrons will move towards the carbon atom and give it a negative charge, whereas Z will have a positive charge. So this is called as the methyl carbanion. Now carbanions are highly reactive, and like carbocations, they are also classified into primary, secondary and tertiary. Now if you remember, when we were talking about carbocations, we said that, we talked about inductive effect. So inductive effect made sure that the positive charge on the carbocation was dispersed, and that in turn stabilized the carbocation. On the other hand, in case of a carbanion, see the carbon which is having the carbanion is basically having a negative charge, and if it is surrounded by electron releasing groups like CH3, then obviously the stability of the carbanion is going to decrease. This because CH3, there are 3 groups which are giving electrons in this case, so the negative charge is going to increase on the already negatively charged carbon atom. And whereas in case of secondary you have only 2, and in case of primary you have just 1. So the positive plus I effect of the alkyl groups is making sure that the electrons are again going to destabilize the already negatively charged carbon of the carbanion. So in this case, the methyl group is going to be more stable, which is more stable than primary, than secondary, than tertiary. So when we're talking about stability, it's just the opposite of carbocation. In case of carbocation, methyl was the least stable, but in case of the carbanion, methyl is the most stable compared to primary, secondary and tertiary. Now when we talk about allylic and benzyl carbanions, we learned about the fact that the benzyl carbocation was stabilized by resonance. Similarly, in this case as well, the benzyl and the allylic carbanions are stabilized by resonance. So CH2 double bond CH single bond CH2. This is the example of an allylic carbanion. So here this negative charge is going to shift to this bond, and this bond, to maintain the tetravalency of carbon, is going to shift to that carbon atom. This leads to a negative charge here, and CH double bond CH2. This leads to the formation of resonance structures. Similarly, in the presence of in case of a benzyl carbanion, so let's take CH2 minus double bonds. So we will be drawing the resonance structures and delocalizing the negative charge. So here will be a negative charge, and then this will shift inwards. This will go to the para position. So the para position is going to have a negative charge, and that will again shift it. Oh, I'm sorry, there's supposed to be the bond here. And so the negative charge goes on to the ortho position. So here you will have a negative charge now, CH2. Obviously this moves in here, this goes there, and so CH2 minus. I'm assuming you already watched the video which we did, where we learned about how to draw resonance structures and what are the various steps that are involved. So our benzyl and allylic carbanions are stabilized by resonance. The next one is, obviously, if there are certain groups like NO2, CN, Cl, COOH, COOR, all of these are electron withdrawing in nature. So if there were such groups in the benzene ring, then obviously they would pull the electrons and they would stabilize the benzyl carbanion. Similarly, had there been groups like CH3 or OCH3, then the benzene would have gotten destabilized. Now, of course, if there are more number of phenyl groups, so here, one thing, I mean, when we talked about primary, secondary, tertiary, we said that there's the difference in order. But even in this case, the phenyl groups, when they are attached to the carbanion, 3 phenyl groups is more stable than 2, which is more stable than 1. So this is again because of resonance effect. The stability of the phenyl carbanions is due to the resonance effect. So let's just there's one more thing. There's the last part, that is about the shape of the carbanion. So carbanion is negatively charged. So here you have an sp3 lone pair, and the shape of the carbanion is tetrahedral and it's negatively charged, and 3 of the 4 sp3 orbitals are basically used for sigma bonds with hydrogen or another set of atoms. Whereas so out of the 4 sp3 orbitals which are present, so there are 4 sp3 orbitals which are present. 3 of them are used for sigma bonds with carbon itself or another atom like hydrogen or some, and whereas the 4th one of them is going to stay with a lone pair of electrons. That is what you write as a negative charge. It has a tetrahedral shape. So carbanion basically has a negative charge. It's formed by heterolytic fission when the carbon atom is bound to an atom which is less electronegative than itself. So the electrons of the bond are going to shift towards the carbon atom, leading it to get a negative charge. The stability in case of carbanion is going to be again explained by inductive effect. However, due to the presence of CH3, which is a plus I group, that leads to the destabilization of the carbanion. So more is the number of CH3 groups, more will be the negative charge on an already negatively charged carbon atom, and this in turn will destabilize, and because of that methyl is more stable than primary, then secondary and tertiary. That is the order. It's the opposite of a carbocation. In case of allylic and benzylic carbanions, they are stabilized by resonance and the rule for resonance is still followed in case of our benzylic carbanions. So more are the number of phenyl groups attached to the carbon, negatively charged carbon, more will be its stability, because more are the number of resonance structures that are present. So in case of if there are certain groups like NO2 or rather CN, Cl, all of these are electron withdrawing nature and they stabilize the benzyl carbanion, whereas electron releasing groups like CH3 or OCH3, all of these tend to release electrons to the benzene ring and they will destabilize the benzyl carbanion. The shape of the carbanion is tetrahedral. It has an sp3 orbital with a lone pair of electrons. So there are 4 sp3 orbitals. 3 of them are going to be used for sigma bonds with other atoms or carbons, and one of the orbital is going to have a lone pair of electrons. So carbanions have a negative charge. They have 8 electrons in carbon atom and they are highly reactive in nature. In the next video, we will be discussing about free radicals. So do check it out.